Okay, now we move on to total parallel resistance. When resistors are connected in parallel, the total resistance of the circuit decreases. The total resistance of a parallel circuit is always less than the value of the smallest resistor. For example, if a 10 ohm resistor and a 100 ohm resistor are connected in parallel, the total resistance is less than 10 ohms. So we're going to start looking at these circuits and look at them and say, okay, we need to calculate the total resistance in this parallel circuit, and I know that the equivalent is going to be smaller than the smallest resistance in the circuit. So in this case, the addition of resistors in parallel reduces the total resistance and increases the total amount of current. In the case where we had one resistor, one total current equals I1, now we've seen that with putting two resistors in a circuit, we end up decreasing the current in both resistors R1 and R2 by an amount that is dependent upon the size of the resistor. So if we look at some of the formula for total parallel resistance, we're going to find that there are some that are general rules that we can use and some that are more specific. So if we look at this first circuit, we can see that a number of resistors, out to the nth resistor is shown. So R1, R2, R3, out to R sub n gives us a total current then that is shown by the number of branches or the number of currents that go through the nodes and split. Since the source is the voltage across each parallel resistor, then by Ohm's law, the current in one is equal to V source divided by R1. I2 is equal to V source divided by R2, and we continue through the ladder. This is called a ladder network. Through the ladder out to R sub n. And so we can see this by this representation then, V sub s over the total resistance is equal to the sum of all of the V sub s over all of the resistors, okay, taken individually. So the term V sub s then can be factored out of the right and the equation and canceled with V sub s on the left, leaving only then the resistor terms. It's because the voltage source is common in every one of these. So we're left with a relationship that says 1 over the total resistance then is equal to the sum of each of the 1 over 1 over 1 over R1 through R sub n. And we saw early on in the course that this really does fit the definition of conductance. The inverse of resistance is, in fact, conductance. So we could simplify this by getting rid of the fractional notation here, the 1 over R, and instead call it conductance. So we've got conductance 1, conductance 2, 3, etc. out to conductance n, summing together to form the total conductance. So if we recall then that the reciprocal of 1 over R is the conductance, then we can use that representation. So now, if we want to solve for the total resistance by taking the reciprocal of that, that is, by inverting both sides of the equation, then we can see that the total resistance then becomes the inversion on both sides 1 over the sum of all of those values. So we can say then that the total resistance then is the total inversion or the reciprocal of the total conductance. So let's look at a simple circuit here. Calculate the total parallel resistance between points A and B. Okay, we've taken out the source. We're just looking at the total resistance. And you can see we've got an array of 147 and 22 ohms in this simple circuit. So what we can do then is we can say, okay, let's first solve for the conductance, the reciprocal of 1 over R. So, excuse me. So we've got 1 over 100, which gives us 10 millisiemens, 1 over 47 ohms, which gives us 21.3 millisiemens, and 1 over 22 ohms, which gives us 45.5 millisiemens. And I'm sure you've all figured out, the easiest way to do this on your calculator when dealing with reciprocals is to use an inverse function. On this Casio calculator, it actually shows up as x to the minus 1, which is up here in the right-hand corner. So if you put in a value like 100 and I hit x over minus 1, I'm going to get 10 to the minus 10 to the minus 3 Siemens. I don't believe this calculator has a 1 over x. Some calculators have a 1 over x representation. On my old Hewlett-Packard, I actually have a 1 over x, and I don't know if you can see it, it's right up here in this corner, a 1 over x representation. So it just depends on what your calculator has. Your calculator on your phone may also have that. So get used to using that. So next, if we calculate the total resistance by adding all of the conductance together, G1, G2, G3, and taking the reciprocal, so now we take 1 over each of those values. We can sum all of them in the denominator now. It gives us a total value, and now when I do the reciprocal, however you do it on your calculator, you end up with a total resistance of 13 ohms. So it seems like we've added extra steps in there in doing these types of calculations, but it actually, even though it's an extra step or two, it actually makes the problem easier, okay? So your text actually gives you a calculator tip. It says parallel resistance formula is easily solved on the calculator using equation 6.2. The general procedure then is to enter the value of resistance 1, take its reciprocal, just like we talked about, by pressing x to the minus 1, which I just showed you. The reciprocal is a secondary function on some calculators. So you may have to push like a secondary key. On my old HP, it's a yellow button. On some of these others, like the Casio, you've got a shift button up here that's identified in, it looks like yellow. So you may have to do that. But this calculator actually has it on the primary function, so you have it directly. So you next press the plus key and then enter R2. So it's just taking you iteratively through each of the values, taking its reciprocal, and repeat this procedure until all the resistor values have in fact been entered. Then press the enter key. The final step is to press the 1 over x key again and enter the key and the enter key to get RT. So you're inverting them all, you're adding them all together, and then in the end, you're inverting it back to RT. So your text actually gives you a nice little demonstration here. Go through that little demonstration, make sure that you understand it using the values from this previous example, run through the example, and get used to using that 1 over x, or that x to the minus 1, in this and other types of problem that involve reciprocals, or problems that are heavily relegated to a reciprocal, or having lots of numbers to add in the denominator. So now what we can do in the simplified case from the general expression is we can look at the case of 2 resistors in parallel, which makes it a lot easier. So we take the previous formulation expression, but now we simplify it down to just 2 resistors, R1 and R2. And we're going to find out later if R1 and R2 are the same value, then it just becomes R, and you can drop the subscript. So combining the terms in the denominator then yields, so all we're doing in the denominator is we're cross-multiplying. We're multiplying both of these expressions by R2 and R1. And so when we cross-multiply in the denominator, we end up with R1 plus R2 divided by the product. So we have a sum over a product. And then what we can do, since it's 1 over, we can invert it one more time, and we have the product over the sum. So this is commonly called the product over the sum relationship. The total resistance for 2 resistors in parallel then is equal to the product of the 2 resistors divided by the sum of the 2 resistors. So this is called the product over the sum relationship. And we can take a quick look at an example here. R1 is 680 ohms. R2 is 330 ohms. And you can see if we put it into the relationship, the product over the sum, we have 680 divided by or multiplied by 330, and then we take the sum in the denominator, 680 plus 330, dividing one into the other. You can see we got 222 ohms. And lo and behold, that total resistance is smaller than the smallest value. The smallest value was 330. The total resistance then becomes 222. Okay? In the case where we have equal value resistors, like I just mentioned, doesn't matter how many they are, if they're all equal value, say in a long ladder, it just becomes simply R over N. So we divide R by the number of resistors. Okay? So if we look at this simple example, if we had 4 8-ohm speakers connected in parallel to the output of an amplifier, which may be common if you're trying to do some impedance matching on an audio system. What is the total resistance across the output of the amplifier? So all I do is I put 8 ohms in the numerator, I divide by 4, and what do I get? A total resistance of 2 ohms, smaller than the smallest. Okay, so when we come back, we're going to look at determining an unknown from a parallel resistor.